Authorization asks a simple but critical question. Once identity is verified, what is allowed? In AI systems, RBAC, ABAC, and PBAC help enforce least privilege across people, services, agents, data, prompts, models, tools, and infrastructure. So far, we've established who the identities are, human and machine, and how they prove themselves through SSO, MFA, passwordless access, and federation. Now we move from verification to permission, what those trusted identities are allowed to do. At decision time, authorization evaluates whether a specific subject, a user, workload, agent, or integration may perform a specific action on a specific AI resource. That resource might be a prompt, vector index, dataset, model endpoint, plugin, or tool. Strong decisions also factor in context, such as device posture, location, approval status, and risk. If authorization is weak, data can be exposed, privileges can escalate, models can be misused, and agents may execute unsafe actions automatically. RBAC simplifies access by placing roles between identities and AI resources. Instead of granting every user, service account, or workload individual permissions, you assign roles that match responsibilities. Each role bundles allowed actions, such as read, write, deploy, or administer. This makes access easier to review and maintain. The design matters. Roles like data scientist or model deployer should be stable, specific, and aligned with real job functions. Role hierarchies reduce administration because a senior role can inherit permissions from several junior roles. But inheritance can also hide risk. If a manager role automatically receives analyst access and later gains deployment rights, that person may reach sensitive data, models, and privileged tools. Least privilege means designing roles around specific tasks, not job titles or convenience labels. Avoid broad roles like AI admin unless they are tightly scoped, and review access regularly as teams and projects change. ABAC shifts authorization from static membership to contextual evaluation. Instead of asking only, what role does this person have, the system asks, who is requesting what, against which resource, under what conditions, and for what purpose. A finance employee may be allowed to read confidential EU data from a managed device during business hours, while an export from an unknown network is blocked. Context makes policies more precise, adaptive, and aligned with real risk. Consider a data scientist requesting access to a healthcare RAG dataset. Their role is only the starting point. ABAC also checks whether the project is approved, whether the data is allowed in their region, whether the device is compliant, and whether the session risk is acceptable. If one condition fails, access can be limited or denied, even for a legitimate user. PBAC centralizes authorization so services do not hard-code rules in every application. A request is intercepted by a policy enforcement point, which asks the policy decision point what to do. The P2P evaluates central policies, enriched by attributes from policy information points, such as user role, device health, risk, or data sensitivity. It returns allow, deny, or conditional access, and the PEP applies that decision consistently wherever the request reaches a protected resource. Policy as code treats authorization rules as software artifacts, versioned, reviewed, tested, and promoted through the same pipeline as application code. A change starts in source control, runs through automated policy tests and realistic access simulations, and requires approval before deployment. If behavior is wrong, rollback is available. The benefit is consistency. OPA, CEDAR, XACML, or Cloud IAM engines can enforce the same intent across cloud, apps, data, and AI workloads. These models work best as layers, not competitors. RBAC gives a clean starting point. Admins, managers, data scientists, each with baseline permissions. ABAC refines those permissions with context, such as data sensitivity, device trust, location, or time. PBAC centralizes the rules so decisions are consistent, auditable, and reusable. In mature AI systems, roles open the door, attributes check the situation, and policies make the final call. Strong authorization is defense in depth. The interface can hide unavailable actions, but it should not be trusted as the control point. Gateways handle broad checks like authentication, tenant boundaries, and request shape. Application services enforce business rules, who may approve, modify, or delegate. Then resource layers, data stores, model endpoints, infrastructure APIs, and agent tools enforce the most specific permissions where damage could occur. Each layer should assume the previous one can fail. RAG changes authorization because users may see protected information indirectly through retrieved chunks or generated answers. Controls need to travel with the data. When documents are chunked and embedded, keep their original permissions and classification as metadata. At query time, filter results by user, group, tenant, project, and region before anything reaches the model. Then validate and audit the answer so teams can trace which sources influenced it. AI systems require two levels of authorization. First, control who can invoke, administer, deploy, or fine-tune a model. Second, control what actions the model's tools can take. A support agent may summarize a ticket and query billing, but not issue a refund or change infrastructure without approval. Delegated permissions should never let the agent exceed the user's own rights. For high-impact actions, add step-up authentication, approvals, or human review. Authorization is not a one-time design choice. It has to operate as a control loop. Log every decision with who acted, what they requested, the resource, context, policy version, and result. Test policies before release against both allowed and denied scenarios. Review access routinely to remove stale roles and unused grants. Then monitor behavior for unusual data access, excessive tool calls, or privilege escalation attempts. That is how authorization stays trustworthy. Authorization turns identity into governed action. RBAC provides a simple starting point, but it needs privilege hygiene. ABAC adds context, including data sensitivity, device posture, location, and risk. PBAC centralizes decisions as code. Next, we apply these patterns to AI, IAM, agent boundaries, secrets, keys, vaults, and short-lived credentials.